Today we're going to look at solving systems by graphing. The kind of systems we're talking about are systems of equations, and that means two or more. And the equations that we're going to be working with are linear equations, which means their graphs are going to be straight lines. Now, before we start, let me just tell you something about what a graph is when we have an equation like this. If I wanted to go ahead and graph this, I have a couple of different strategies. And maybe what I'll do is I'll illustrate with an example. So this would be our system of equations. So we have two equations here. And I'm going to go ahead and graph the top equation. And I'm going to use one method, which is to just find a couple of points that make this equation true. In other words, I'm going to look at this equation, and I think it's very easy for me to see that if x was 4 and y was 0, that this works. 4 minus 0 equals 4. That's going to be a point on this line. All I need is one more point, and then that I can connect the 2 points and draw my graph. So the other line, the other point would be something like, how about 6 take away 2? Okay, so I've got 2 points, and I'm going to go ahead and graph those 2 points. On the one hand, we have 4, 0, and on the other hand, we have 6 and 2. So 4, 5, 6, and up 2. Those are 2 points on the line, so I connect the 2 points, and there's my graph. Now understand that what a line is, when we graph a line like this, that these are 2 points that we found by kind of inspecting the equation, whose coordinates work, they make the equation true. Well, what a line is, it's literally millions of points, billions of points, that also make the equation true. Every point on the line has one thing in common. When you plug in their coordinates for x and for y, they end up making the left side equal the right side. And that's really what a graph is. It's a collection of all points that make the equation true. Now, I might find a couple of points easily with this equation, but it's also possible that it may be a big challenge to find more than 1 point. And so I'm going to use a totally different method to graph the second line. I'm going to put it into slope-intercept form. Now, you might remember slope-intercept form looks like this. Y equals mx plus b. M is the slope, and b is the y-intercept. So all I have to do is rearrange this equation to get y equals and read off the slope and the y-intercept, and then graph it. So I'm going to move the 3x to the other side, so that will leave me with 2y equals negative 3x plus 7. And then I'm going to divide everything by 2. So I'm going to get y equals, this will be negative 3 over 2x plus 7, also divided by 2. Now this one's a little bit strange to graph, but we can still graph it nonetheless. The y-intercept is 7/2, which would be 3.5. So I'm going to go up to 3.5, so 1, 2, 3.5. That's where the line crosses on the y-axis. And I need to construct a slope of negative 3/2. So I'm going to think of that as negative 3 over 2. So kind of a negative rise and then a run of 2. So from here I'm going to go down 1, 2, 3, which takes me to 1/2. And then I'm going to go over 2 spots, 1, 2. And then I just join up the dots, and I've got my second graph. And now we're ready to make our analysis and what we believe the solution is. What we're looking for when we're given a system of linear equations is a point that makes this equation true, but also makes this equation true. And there is, from our graph, only one such point, and that is where the two lines cross. This is the only point that is on both of the lines, which means only this point's coordinates, when I substitute them into this equation and this equation, work. So what are the coordinates? Well, our solution looks to be 3, -1. And what we want to do is confirm that this actually does work. If I put in a 3 and a -1, does this equal 4? Well, the answer is yes, it does. So this equals the right side. And now let's try our so-called solution on the other equation. So 3 times 3 plus 2 times -1. Does that equal 7? Let's see. 9 and -2. Yes, it does. It does equal 7. And this is the only such point whose coordinates work for both equations. Okay. That's our first example. And what I'm going to do is talk about some of the situations that can occur when you're looking for solutions, because they don't always necessarily have solutions. So I'm just going to clear off a little board space here and talk about those different situations. What we've seen here is a situation where the two lines cross. So first scenario is lines cross and you have one solution, and that is your intersection point. Another situation that can occur is that the lines are parallel. If you have parallel lines, they never cross. So they have no point in common. That means no solutions. And lastly, another situation which is kind of a strange one, and that is that the lines are what we call coincident lines. Now, coincident lines really mean the equations looked deceptively different, but when we graphed them, it was really one line and the other line's right over top of it. So it's really the same line. What that means is we have infinite solutions, which means there are so many points of intersection that there's too many to count. So this little symbol means infinite, or billions upon billions of solutions. So how do we know which is which? This is where it is very useful to put the equations into slope-intercept form. If you do that, a simple comparison of the slopes and the intercepts will pretty much tell you which category you're in. So put equations into this form, y equals mx plus b, slope-intercept form. So let me just do a couple examples of that and show you how we can find the solutions graphically, or analyze that there really are no solutions, or perhaps infinite solutions. So in this example, I think what I'm going to do is 3x plus y equals 1, and 6x plus 2y equals 2. So I'm going to proceed and have a look. What I'm going to do is put each equation in a slope-intercept form. So let's start with the first one. This one is very nice. All I have to do is subtract 3x to the right side. So that equation now looks like this. Negative 3x plus 1. I'm going to do the same thing to this one. I'm going to move the 6x over. So what we have is 2y remaining on the left. That equals negative 6x plus 2. But I've got to divide everything by the 2 now. So dividing by 2 gives me negative 3x plus 1. Well, what do we have? These two lines are identical. So if they're the same lines, then they're going to be coincident, which means infinite solutions. So we know we really got two lines may have looked different, but they're the same. Okay? Let's go to another example. In this one, we'll have 2x plus y equals 4, and x plus 2y equals 6. Now, what we would do, again, I'm going to put these into slope-intercept form. And so this one's quite easy. The top one, we're simply going to subtract the 2x over. So we're going to end up with negative 2x plus 4. And this one here, we're going to move the x over, and then we'll have to divide by the 2. So what do we have? 2y, negative x plus 6, and then divide by 2. So this would become negative 1/2 x, and then 6 divided by 2 is 3. Well, the slopes are different. The y-intercepts are different. So these are very different lines, which means we're going to have one solution. And to get that solution graphically, I simply have to go and graph each line and kind of estimate that intersection point. We'll start with the top one. It goes through 4. And it has a slope of negative 2. Think of that as negative 2 over 1. So that means down 2 and over 1. So that line looks something like that. The other line here has a y-intercept of positive 3. And it has a slope of negative 1/2. So I like to make it very clear. I think of the top as negative, the bottom positive, to get my negative 1/2. So down 1 and over 2. And so that line looks something like that. And so now my solution is their point of intersection, which looks to be about 1/2. And we're a little bit lower than 3 here. I'm going to estimate that to be something like 2.5, I guess. Now, that's the one problem with the graphing method. Can't always tell exactly what that solution is supposed to be. So you do the best you can. So that was that one. Let's look at my last example now. What if we have something like this? 3x plus y equals 7. And this equation here could be negative 6x minus 2y equals 4. Okay. So let's put them into slope-intercept form. We'll bring the 3x over. Again, the top one, nice and simple. We end up with y equals negative 3x plus 7. The bottom one will require a bit more work. So I'm going to bring over the 6x. Now that leaves me with a negative 2y on the left. This becomes positive 6x plus 4. And then divide by negative 2. So this is going to become 6 divided by negative 2 is negative 3x. And then minus, this is 4 divided by the 2, so minus 2. And what do we have happening here? Same slopes, but different y-intercepts. And what that means is no solutions. You've got a y-intercept of 7 and a slope of negative 3. So we'll think of that as down 3 over 1. And when we go to the other equation, it has a y-intercept of negative 2, but the same slope, negative 3. So go down 3 and over 1. What you have happening here are parallel lines. So there is no intersection point, i.e. no solution. Okay? And that's my conclusion of solving systems by graphing.